So we're going to finish up chapter 3 today with this last video. In this video, we're going to start off with talking about unusual values. So if the standard deviation is known, it can be used to determine whether data values can be considered unusual using the following rule of thumb. So it says minimum usual value equals the mean minus 2 standard deviations, and the maximum usual value equals the mean plus 2 times the standard deviation. So basically, you think of it as you find the mean, and then you find the standard deviation, okay? And you think of it like you're walking left and right of the mean. You're allowed to go 2 standard deviations to the left of the mean, and you're allowed to go 2 standard deviations to the right of the mean, or plus or minus. And anything in there is considered usual, and anything outside of there is considered unusual. So let's look at example 11. It says, past pulse rates from the National Health Survey suggest that the pulse rates beats per minute have a mean of 76 and a standard deviation of 12.5. Use the rule of thumb to find the minimum and maximum usual pulse rates. Then determine whether the pulse rate of 110 would be considered unusual. Okay, so what we're going to do is we're going to find the minimum usual, and we're going to find the max usual. I guess we can use equals. So they said that the pulse rates, Surgery says the pulse rates have a mean of 76. So they said that the mean is 76, and now we're going to minus 2 times the standard deviation, but the standard deviation is 12.5. And then for the max, we're going to do 76 plus 2 times 12.5. So let's see what we get from these two. So I'm going to take out my calculator, and I'm going to do 76 minus 2 times 12.5. So I get 51. And then I get 76 plus 2 times 12.5, and I get 101, okay? So that means beats per minute. So that means that any number, hold on real quick, you guys. What bad timing is that? My dog started going crazy. I'm sorry about that. So anytime that you found your minimum usual and your maximum usual, you now have like a window that any value in between these two numbers is considered like a usual, kind of like what you expect to happen, something like that, nothing strange. But anything outside of these is considered unusual, okay? So they said, determine whether the pulse rates of 110 would be considered unusual. We would say yes, 110 beats per minute is unusual. Since it is above our maximum usual value of 101. Okay. All right. So let's see here. Hopefully that makes sense to you guys. So now let's talk about something called the empirical rule. Now the empirical rule, how do I say this? It works really well, and it's really nice if everything lines up perfectly. If you have 1 standard deviation, 2 standard deviation, 3 standard deviations, the empirical rule works really well. In chapter 6, we'll be able to use something more than the empirical rule. We're still kind of using it, but we now know how, by that time, we'll know how to work with normal distribution much better. It says for data that is bell-shaped and symmetric, there is a rule that is helpful interpreting values of distribution and percent of values accounted for above, below, or in between values of data. So if the data, now again, this is for data. Now I want you guys to keep this in mind. This is for data that is bell-shaped and symmetric. So basically, something like this or like this, okay? We're not going to use this one for our class. Not to say there's anything, wrong with it, but for our class, we're going to kind of keep it strictly to something like this. Sorry about that. So what we're going to do is it says that 68% of the observations fall within 1 standard deviation of the mean. 95% of the observations fall within 2 standard deviations of the mean. And approximately 99.7% of the observations fall within 3 standard deviations of the mean. So if we come over here, we look at this problem. It says IQ scores have a bell-shaped distribution with a mean of 100 and a standard deviation of 15. So they're telling us we're allowed to use the empirical rule. Okay, so what I'm going to do is I'm going to draw my little bell shape for myself. Okay, let me draw it a little bigger. Okay, and it's supposed to be symmetric. I may not have drawn it right, but you guys get the idea. And it says, IQ scores have a bell-shaped distribution with a mean of 100. So that means right here, smack dab in the middle, that's the mean of 100, right? And a standard deviation of 15. So that means that I got to walk about to here and about to here. And that distance should be 15, right? Because that's how far I'm going. So that means this will be 115, and that means this will be 85, right? If I walk 15 to the left and 15 to the right. Then I'm going to walk another 15 and another 15. And again, this is supposed to be symmetric, but I can't draw. So this will be 70, and this will be 130. Then I'm going to walk again, and I'm going to do another 15, and this will be 55. And I'm going to walk another 15, and this will be 145. So what this is now telling me, that if I shade in here, how much of the observations, or how many IQ scores, what percentage of the 100, or I'm sorry, what percentage of the IQ scores would I expect to be in there? Well, according to the empirical rule, 68% should be in there, right? That's what it says. Okay, so from here to here should be 68%. All right. Now, what if I shade even further, all the way to there and all the way to there? What does the empirical rule say now? Well, the empirical rule now says that, geez, it's going to be hard to draw. So from here to here, right, it's now saying, let me draw it off over here, that it should be 95%, right? So I'm looking up here, that's what it says right here. 95% will be within 2 standard deviations. And you guys see I walk 2 standard deviations to the left and 2 standard deviations to the right. Now let's go even further. Let's go here to here. So now what does the empirical rule say about from here to here? How much of the observations, or how much of the data should fall within 3 standard deviations? Well, the empirical rule says it should be 99.7 approximately. So we should have, we should have for this one, 99.7% of all data should be in between 3 standard deviations both ways. Okay, so if you go 3 standard deviations to the left and 3 standard deviations to the right, that should account for 99.7% of all the observations or the data. Okay, so let's read the next question. It says, according to the empirical, what percentage of IQ scores are between 70 and 130? So what I'm going to do is I'm going to say, look right here. I am at 70 and I'm at 130. How much of the data should be right there according to the empirical rule? Well, we said 95%, right? The empirical rule tells us that. No work. This picture tells me everything I need to know, okay? Now, according to the empirical rule, what percentage of IQ scores are above 145? Well, here's 145 right here, right? Here's 145. How much data should be over here? What amount? Well, we know that the total is 99.7 in between 55 and 145. So we might say, well, wouldn't we just do 100% minus 99.7%? And we would get 0.3%. Okay. Yeah, 0.3%. Okay. However, there's a slight problem with this. You guys, I need you to understand something, that first of all, 0.3% is really 0.003. Let me do this a little bit better. So I'm going to convert 99.7 to a decimal. So that means it's going to be 0.997, and I'm going to do 100%, which is 1, right? I'm going to convert these both to decimals instead of doing 100 minus 99.7. So I'm going to do on my calculator 100 minus 1 minus 0.997. So I get 0.003. Okay. So it says, according to the Bureau, what percentage of IQ scores? I guess I kind of screwed up. I'm going to end up having to convert it back to percent. I should have done it right the first time. I'm sorry, guys. Sorry about that. I thought they wanted decimal. I didn't read the question correctly. It says what percentage. So I'm going to say 100% because you guys all understand that the whole graph is going to be 100%, right? All of the data falls somewhere on this graph. But the empirical rule says that within 3 standard deviations, 99.7% of all the data should be there. So I'm going to do 100% minus 99.7. I'm just going to leave it in terms of percent. So I would get 0.3 of 1%. So not even 1%, but this is actually wrong because notice that, right, notice that, oops, this data and this data over here, all of that combined counts for 0.3%. But they're saying how many of the IQ scores are above 145. So we only get to use one side. And since it's symmetric, I know that what I have to do then is divide this by 2. So this would actually become 0.15%. Remember, it's symmetric. So what's above 145 is only half of what's above 145 and below 55, right? So I only get to say 0.1, not 15%. This is 0.15 of a percent, or a 1/1500th of 1%. Okay, so this is a very small value. All right, so 3.4, this will be, I believe, what do we got? 2 pages, 3 pages. Yeah, so 3.4 is the last section we're going to cover. I think in your homework, it'll be called 3.3. Remember, the numbering of the book is slightly off from the pages in the notes. It's normally off by 1 section. Okay, so something really important that's going to be a core foundation of this class is called a Z-score. So it says, if we wish to compare data in different data sets or within the same data set, we need some measure of relative standing. Measures of relative standing tell us where particular data values stand in relation to other data values in its set. So a Z-score is the number of standard deviations that a given observation value X is above or below the mean. This value standardizes the values so that they can be compared. So basically, the Z-score is a way that we can talk about standard deviations. So if I told you that your Z-score was 3 standard deviations above the mean, that's a big deal because you don't even need to know what you got on the test. You know you did amazing. Because if the mean is the average and your 3 standard deviations, look up here. Look how far. 3 standard deviations is right here. What the heck percentage did you get on the exam to be in the top, above 3 standard deviations? That means you're beyond 3 standard deviations. So without me even telling you, I could just say, hey, your Z-score is 3.4. You throw a party because that means you scored very well on the exam. You were above the normal or above the average class by 3 standard deviations, a little bit more. That probably means you got like a 99.5 or something, some amazing score on an exam. Okay. So Z-scores tell you how many standard deviations you are away. Now they could be positive or they could be negative. Remember, standard deviation is always positive. A Z-score is talking about how many standard deviations. So when it's negative, it just means that you go to the left of the mean. If it's positive, that means you go to the right of the mean, that many standard deviations. So a Z-score within 2 standard deviations is ordinary, and outside 2 standard deviations is unusual. So this is another way that we can talk about usual versus unusual just by looking at Z-scores. So in order to find a Z-score, if you're dealing with a sample, which we often will be, Z is equal to X minus X bar divided by S. And for population, it's Z is equal to X minus mu divided by sigma, or standard deviation of the population. So I think what's best is if we go over one of these. So the distribution, in example 13, the distribution of heights of women aged 20 to 29 is approximately bell-shaped. Again, meaning normal, so meaning that we can use Z-scores. Remember, Z-scores are used with normal distribution in general. That's the only time we really talk about them, or approximately normal. So it says, the distribution of heights of women aged 20 to 29 is approximately bell-shaped or normal, with a mean of 64 inches and a standard deviation of 2.7 inches. Men the same age have heights that follow an approximately normal distribution, with a mean height of 69.3 and a standard deviation of 2.8 inches. what are the Z-scores for women who are 6 feet tall and for a woman who is 6 feet tall and for a man who is 6 feet tall? So we want to find out the Z-scores, and then we want to, based on the Z-score, make a prediction and see if it's unusual or usual for a female to be 6 feet tall or for a man to be 6 feet tall. So the first thing we're going to do is we're going to use this formula. So we'll do women first. Okay. So we have Z equals, now they said a woman who is 6 feet tall, but remember 6 feet is 72 inches. And since they gave us the mean in terms of inches, we should convert everything we're doing to inches as well. So this will be our X in this case is 6 feet, but that's really 72 inches. So we're going to do X is 72 minus the mean, but they said the mean is 64 for women, right? Let me see, for women is 64 inches. And then we divide it by the standard deviation of 2.7. And we can do men over here. So the Z-score for men, or for a man who is 6 feet tall, we're going to do 72 inches minus, now the mean of men is 69.3. I got it from right here. And then divide that by the standard deviation of 2.8. Okay, so on our calculators, we're going to do an approximation with this. So our calculator is 72 minus 64, enter, and then I hit divided by 2.7. So I get 2.963 if I round off to, let's do 3 decimal places. So I get 2.963. Okay, and then on this one, let's do males or men, is 72 minus 69.3 divided by 2.8, and I get 0.964. Okay, so for men, the Z-score is 0.964. So for men, we have a 0.964 Z-score, and for women, we have a 2.96. Okay, is it unusual for a female to be 6 feet tall? Yes, it is. Oops. Unusual for a woman to be 6 feet tall, since her Z-score is above 2. Remember, anything above 2, a Z-score above 2 or below -2 means that it's unusual, okay? Right here, it says that right here, more than 2 standard deviations, okay? So Z-scores, since they represent standard deviations, any Z-score that's above 2 is considered unusual, and any Z-score below -2 is considered unusual. It is not unusual for a man to be 6 feet tall, since the Z-score is around 1, which is definitely within 2. Okay, so that's how you can use Z-scores for this type of information. Okay, so something else that we have to talk about is percentile measures of location, denoted P1, P2, P3, all the way to P99. This symbolizes, what percentage of the data, so which divide the set of data into 100 groups, all with 1% values in each group, or all about 1% of the value of each group. So it says finding the percentile of data values. The process of finding percentile that corresponds to a particular data value X is given by the following. So the percentile of value X is equal to the number of values less than X divided by the total number of values times 100. Okay, so this is just a notation that they want you to get comfortable working with. Okay, so what we're going to do, is we're just going to follow the instructions that they gave us, right? So it says number of values less than X. Okay, so let's see here. They said, again, refer to the following data for weight gain in pounds of 10 women during pregnancy. Okay, so find the percentile of women who gained 37 pounds. Okay, So this says percentile of women, number of values less than X. Okay, so let's see here. This one is less than 37. This one is less than 37. This one is less than 37. And this one is less than 37. So number of values less than X. And in this case, X is 37, right? So we only want the values less than X. So there's 4 of them. And then it says divided by the total number of values. Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 4 divided by 10 times 100 equals, so this would be 0.4 times 100 equals 40%. So the notation is P sub 40 is equal to 37. So the number 37 is the 40th percentile, and that's just a new notation they want to write, okay? Does that make sense? If this is something you want to talk to me about in class, we can, but this is just a notation. So when you see P sub 35, this means that whatever number this is, it is in the data value, whatever it may be, is in the 35th percentile. So this is just a notation that we use to write that. We're not going to go too crazy in this, but it'll come up in random spots throughout the course, okay? So here we have, find the data value corresponding to a certain percentile P sub K. Let me see. They want to know P sub 10. So I'm not going to spend too much time on this. I'm just going to kind of go through it. So if it comes up in the homework, but I don't know if I'm probably not going to test you guys on this. So it says find the data value corresponding to a certain percentile. So it says L is equal to K divided by 100 times N, where K is the percentile and N is the number of data values. So in this case, P sub 10, so we're going to say L equals, what do they say? K is the percentile. So we know that this is 10 divided by 100 times N. And N is the number of data values. So let me see here, function. A study was done on 16 middle-aged runners. So it should be times 16. And we end up getting, let me see here. So that's 1/10. So that should be 1.6, right? And then there is no 1.6. So we're going to round up to 2. So that means that we're looking for the second data piece, which would be this one, right? Because 16 is the second data piece. So that means L. So we're going to locate the position. So round L to the next whole number. So I did what they said here, round L to the next, count to that location in the ordered data set. That data value is P sub K. So P sub 10 is, or P 10th percentile is 16 for this particular problem. So now we could do P sub 80. So we're going to do L is equal to, now we're going to do 80 divided by 100 times 16 again. So we're going to do 0.8 times 16, and we get 12.8. But we're going to round this up to 13. So now we count the 13th number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it's 24. So that means P sub 80 is worth 24. So that's how you can do it for these particular problems. This L is a way that you can find the number in the list, and then you count to that number, and that is your 80th percentile or your 10th percentile or your 20th percentile or whatever the case may be. If I ask you one of these, it would be something very straightforward like this, nothing too crazy, okay? So now what we're going to talk about is quartiles. Quartiles are data values that split the data set into quarters when ordered from least to greatest. The first quartile is the midpoint between the first observation and the median, the 25th percentile. The second quartile, Q2, is called the 50th percentile or the median. And quartile 3, Q3, is the midpoint between the median of the last observation, midpoint of the last observation. So the median and the last observation, that's called the 75th percentile. So how to determine quartiles. Arrange the observations in order from least to greatest. So that's pretty much, we're used to doing that. Locate the median M in the ordered list. The median M is the second quartile. So they don't really use Q2. They oftentimes just call it the median. The first quartile is the midpoint between the first observation and the median. And the third quartile is the midpoint between the last observation and the median. Now, this is something specific to statistics called the Interquartile Range, or IQR. Is a common measure of variation or spread, which is found by subtracting the first quartile from the third quartile. So we'll do that together. So what I'd like you guys to do is, so we have a sample of 20 travel times of those who work in New York are ordered below. Okay, so they put them in order for us just to save us a little time. And it says find the quartiles and calculate the IQR. Well, let's see here. There is 20 times. So that means that if we wanted to find the median, remember the median? So there'd be 21. Remember, it's 20 plus 1 divided by 2. So this would be 21. So this would be 10.5. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. And we find what's in the middle right here. So what's in the middle right there is 22.5. And all you have to do is you could just take 20 plus 25 and divide by 2, and you would get 45 divided by 2, which is 22.5. So that's how I found that, okay? Now I have to find the median of that. So there's 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so now I want to find the median of that. So then that would be 15.5. Oh no, that would just be 15. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that would be right here. Quartile 1 is 15. This is quartile 2, or median. And now we have to go 1, 2, 3, 4, 5. So that would be right here. So we get 42.5. That would be quartile 3, okay? Now what you can do is they then want to know the IQR. The IQR is equal to quartile 3 minus quartile 1, okay? So quartile 3 is 42.5 minus quartile 1, which is 15. And we should get 27.5. This is our IQR. And it won't matter to us just yet. It'll make more sense when we're talking about outliers, okay? So let's actually do a problem like this. Oh, by the way, I'd like you guys to take out your calculators. Okay. So sorry, I should have had this brought up already. Sorry about that. So take out your calculators. And let's enter all this data in, okay? So what I'm gonna do is I'm gonna go into Stat and Edit, and I'm gonna clear this list, okay? So now I'm gonna enter in all of this data. So I'm gonna do 5, 10, 10. You guys can probably do it faster than me. The touchscreen isn't as fast as a calculator. 15, 2 more 15s. Let's see, 20, 20, and 20. So 20, 20, 20, 25, 30, 30, 25, 30, 30. Hopefully I don't enter anything wrong. 40, 40, 45, 60, 60, 65, 85. Hopefully that's it. Yeah, 21. Or there's 20 of them, okay? So now I'm going to quit. Now I'm going to go into, let me clear this, Stat, and now I'm going to go into Calculate. Single variable stats, and we've done this before. Calculate list 1, frequency list, don't worry about that, and hit Calculate. Now, this is all the stuff I showed you before, but if you scroll down, do you guys see where it says Q1 median, Q3 max, min? This is called the 5-number summary. So starting at the min X all the way up to max 5, those are 5 numbers. This is called the 5-number summary. So you notice that quartile 1 is 15, the median is 22.5, and Q3 is 42.5. That's exactly what we just did the other way. So I would recommend using the calculator. It's much more reliable than kind of counting and then trying to do it. It's just a little bit cumbersome and annoying. The calculator is pretty quick. So this is how you can enter in a list of data into your calculator and then find the 5-number summary, which will give you the quartile 1, the median, and quartile 3. Okay, so let's look at the next problem. I'll leave that open. We may need that again. So now it says the 5-number summary. The 5-number summary of distribution consists of the smallest observation, which is the minimum, the first quartile, the median, the third quartile, and the largest observation. So this is the 5-number summary right here. Okay. Once you have the 5-number summary, these numbers can be used to construct a box plot. So we're going to work with a box plot. So it says a regular skeletal box plot is a graph of data sets that consists of a line extending from the minimum to the maximum line. We normally call those whiskers, and has a box bounded by the first quartile and the third quartile. There is a line in the middle of the box where the median is. Okay. So this is basically what a box plot looks like right here. Annual snow depth at Mathville Ski Resort. Okay. I didn't write all these notes, so some of the jokes. All right. So it says the procedure for constructing a box plot, okay? So one thing it's important to understand, a box plot and quartiles. Remember, quartiles are talking about 25th percentile, 50th percentile, 75th percentile. They're called quartiles because it's like cutting up things into quarters, right? So don't let it freak you out. It sounds fancy, but it's really no big deal, okay? So it says here are a sample of 15 workers from North Carolina. Workers from North Carolina have travel times and they're given in order below. So let's find the normal or the 5-number summary, and I'm going to use my calculator. So here we go. I'm going to go into y equals, oops, sorry, wrong thing. Mode, I don't know why it's in that. Second, quit. Okay, let's go into stat, edit, and it's going to go 5, 10, 10, 10. So some of the similar data values, but not all of them are the same. Okay, so let's see here. The next one is 10. The next one is 10. 12, 15, 20. 12, 15, 20, 20, 25, 30, 30, 40, 40, 60. Okay, so let's clear that one. Oh, don't tell me. Oh, delete. Uh-oh. Oh, geez. Okay, guys, I guess I can't do it like that. I have to start over. Sorry about that. Okay, so let's go clear and then down, and that wipes it. Okay, so let's do that again. 5, 10, 10, 10, 10, 12, 15, 20, 20, 25, 20, 20, 25, 30, 30, 40, 40, 60. Okay, so now we quit, and now we go into stat again, and then this time we go into calculate, single variable, calculate. Now we're going to scroll down, okay? So notice, write down your min, your Q1, your median, your Q3, and your max. So 5, 10, 20, 30, and 60. So I'm going to go back here, and I'm going to write down my 5-number summary. So my min equals 5, my Q1, you know what, let me write it over here. So my min equals 5, my Q1 equals 10. This is from the calculator again. My median equals 20. My Q3 equals 30. And my max, geez, I still can't fit it. My max equals 60. This is my 5-number summary. Okay, So now you can use this to construct a box plot. So what I'm going to do is I'm going to take and I'm going to draw my minimum of 5. That's right about here, right? And then I'm going to take my maximum of 60. That's right about here, right? Okay. And now I have to do quartile 1 of 10, but I draw these bigger this time. I draw these bigger like that. And then, you know what? I'll even do it like this. There's 10. My median is 20. And my Q3 is 30. Okay. And I connect these and I make my box. So this is my box. And then these guys are called whiskers, your min to your max. These guys are called whiskers. Okay. So that's how you construct a box plot. You just write down these 5 number summaries. You put lines right there, and you create a box plot. And now this right here, this is, right, that is Q3, and this is Q1, right? And you could subtract those 2 numbers, and you could get your IQR if asked. So my IQR is Q3 minus Q1. So this would be 30 minus 10, which would be 20. So I have an IQR of 20, an interquartile range, okay? So this looks slightly skewed, right? It looks like the tail is longer on the right, so this would be a right skewed graph. There's more data kind of shifted to the left, all right? Okay, now the thing is in the next page, it talks to us about trying to find outliers, and they say that you build your lower fence and you build your upper fence, and anything outside of that is an observation is below the lower fence, it is an outlier, and if it is above the upper fence, it is an outlier. So this is now how we can definitively describe an outlier using a box plot. Okay, so I'm going to build in the previous problem Q1 minus 1.5 times the IQR and Q3 plus 1.5 times the IQR. Okay, so here we go. We're going to find if 60 is an outlier. So find if the observation 60 is an outlier. Okay, so here's what we're going to do. We're going to find our lower fence, which equals, and remember, I'm just going to go back here and it says Q1 minus 1.5 times the IQR. So Q1, which we know is 10, minus 1.5 times 20, which is our IQR. So I'm going to do 10 minus 1.5 times 20. So I get negative 20. Okay, so we don't have to worry about that. Now let's do our upper fence because the number we're talking about is on the higher side, right? So our lower value of 5 is definitely not an outlier because it's within negative 20. So what you can do is you can think about this as your lower fence. Your lower fence kind of tells you, you know, we can go all the way here to negative 20. So any values that are inside of that are totally fine, right? Any values that are above negative 20 are not considered outliers. Now we go back over here. Now we find our upper. And our upper fence says that we take our quartile 3 and we add 1.5 times our IQR. So we're going to do 30 plus 1.5 times 20, and I get 60. So because 60 is actually on the fence, so since 60 is on the fence, it is not an outlier, even though it really feels like it is. But if we go to the rules, right here it says, if an observation is below or if an observation is above, 60 is not above the upper fence, it is the fence. So then it is not an outlier, okay? So this is how you can do it. If there is an outlier in the data set, the box plot is modified to reflect the outlier. Outliers are to be marked with an open circle on the box plot. The whisker of the box plot then extends to the next highest or lowest data value, which is not an outlier, okay? So we can go here to modified box plots. So let's try this one. So once again, let's enter this data into our calculator. So we're going to go into Stat, Edit. I'm going to clear my data. Okay, and I'm going to enter in this new box plot. Okay. So we now have the New York problem revisited. 5, 10, 10, 15, 15, oops, 15, 15, I think there was 4 of them, right? Yeah, and then 320, so 20, 20, 20, and then 25, 30, 30, 25, 30, 30, 40, 40, 45, 60, 60, 65, 85. Okay, so now we're going to quit, and now we're going to go to Stat, Calculate, Single Variable Stats. Okay, we'll scroll down to get our 5-number summary. So we're back to our problem with our 5-number summary. Okay, so this is the information that we had before. So I'm going to write out my 5-number summary. And this time we know our min is 5. Our Q1 equals 15. Our Q2, but we don't do Q2, we write it as median. Our median is 22.5. Our Q3 is 42.5. And our max, I'll write it over here. Keep running out of room. Our max is 85. So in order to draw, let's draw our box plot real quick. So we're going to take 5. So we're going to put 5 right here, right? This is 5. And then we're going to do Q1, which is 15. So that's right here. Okay. And then median is 22.5. So I would assume that's right about here somewhere. So this is 22.5. This is 15. And then Q3 is 42.5. So I would assume that's right about here somewhere. And then our max is 85. So 85 is over here. So then I would draw my box plot like this, right? And I would have my whisker and my whisker. And as you can tell, it probably looks like 5 is okay, but 85 might be an outlier. So this is 85. We're going to have to double check that guy. So what I'm going to do is the first thing I need to do is I need to build my lower fence and my upper fence, but that means I need my IQR. So my IQR equals 42.5 minus 15. So we have 42.5 minus 15, and we get 27.5, okay? And again, this is also the problem we did over here, right? So this is the same problem as here, but now we're doing more with it. We're creating a modified box plot if necessary. Okay, so that means that we can find our lower fence and our upper fence. And this will help us determine if there is an outlier. So the lower fence is 15 quartile 1 minus 1.5 times the IQR. So I'm going to do 15 minus 1.5 times 27.5, and I get negative 26.25. So 5 is definitely okay. We don't even have to worry about it. It's not an outlier because it's definitely within the fence, right? So the fence is way over here at negative 26.25. So right, if we wanted to build like a fence where everything belongs, we have to, we have to kind of see where this guy's going to go. Okay, so now we need the other side, the upper fence. So the upper fence will be quartile 3, which is 42.5 plus 1.5 times the IQR, which is 27.5. So this is 42.5 plus 1.5 times 27.5. So I get 83.75. So that means that 85 is in fact an outlier because it's above the upper fence. So 85 is outside or above, outside of the upper fence. So it is an outlier. Now what they want you to do in a modified box plot then is we erase this. We put like a little star right here, at 85 and we label it outlier. And then the next highest value, which would be 65, which is inside the fence, that's our new whisker, and we draw our graph, right? So this is our modified box plot, okay? And then means our fence, because our fence goes all the way up to 83.5, right? And 85 is just a little above that. So that's how you create a modified box plot, okay? So that is everything in chapter 3. So hopefully you guys can get started on the homework for this. But I just wanted to give you guys a few examples of box plots. And remember, they're percentiles. So, you know, 25% of the data is in here, 25% of the data is in here, 25% of the data is here, and 25% of the data is in here. So between the min and quartile 1, there's 25% of the data, and then quartile 1 to the median is 25% of the data, and then quartile 2 to quartile 3 is 20, so on and so on. So it's, you really have to think about how the box plot represents like data values, okay? So just to give you guys a heads up, I think in your homework there might be 1 or 2 box plots, and maybe on the quiz as well. All right, you guys, that's going to do it for chapter 3. Be on the lookout for chapter 4 videos. Thanks for watching.